Hi, today I'd like to talk about how to drive an LED. What? So you know what an LED is? That it's used in a toaster to the backlight of a LCD TV? That a single LED has two legs and it comes in through-hole and SMD packages and a variety of different colors, and it's basically a diode that the current can flow in one direction through? Yeah, you think you know everything? Then tell me, what is event horizon and its relationship to an LED? I thought so. Now sit down and listen. Good. By the way, video is sponsored by Audible, where you can listen to anything you like. New members can try Audible for free for 30 days from the link in the description. More at the end. Now yell your answers at the screen. Can we drive diodes with DC or AC? You're all wrong. The answer is maybe. Of course you can drive it with both DC and AC. LED or light emitting diode is a diode, which means it sends the electric current through in one direction and blocks the current from going back. If you'd like to know how a diode works, I made a full video about it. Go watch that. Oh, you're back? Okay, so LEDs, when the current passes through them, emit light. That's why they are light emitting diode. Now you might say current going in one direction only sounds like DC. So I have to show you that LEDs actually run on AC. I just need an AC source. Of course, everyone has an AC source at home. I just tied an LED to the end of my power line and I plug it in. What, it's not gonna... Not all components blow in spectacular ways. Just because you don't see the sign doesn't mean the high voltage is not there. So the LED blew for two reasons. The current was above its limit and the reverse voltage was above its limit. So if you look at the datasheet of an LED, you see that for this one, the continuous forward current is 30 milliamps and the reverse voltage is 5 volts. You don't put any limiting components on your LEDs, they are sure to die. Although not in spectacular ways. Another bit of information looking at the datasheet is that when the LED is on, there is typically some forward voltage across it, which for white and blue LEDs is around 3 to 4 volts, and for the other colors it's around 2 volts. So knowing that, looking at the voltage current curve, like any other diode, when the forward voltage of an LED passes some threshold, the current through it exponentially spikes up. So with a little bit of voltage change, you get massive current change. So basically, the voltage across the LED is pretty much fixed for a large range of current through it. And putting a large reverse voltage across the LED, larger than the breakdown voltage, will also result in the diode conducting large amounts of current, and both cases can overpower the LED and burn it, which is what happened when I placed 120 volt AC across it. To limit the current through the LED, we can put a resistor series to it. So for example, if we have a source voltage of 5 volts and LED has a forward voltage of say 3 volts and we want 10 milliamps through the LED, the resistor would be 200 ohms. Fine, let's drive our LED from DC first. Such a weak bullshit. Here's my LED series with 220 ohms and a 5 volt supply. Doesn't even turn on. I probably connected backwards. There you go. It's on. Yay. Is this what you want your life to be? An uninteresting, boring... What's the use of all this knowledge if we can't directly drive them from the AC 120 volts? So let's do that. Here we go. I put 5.6 kilo ohms series with the LED for around 20 milliamps and brighter light. Here we go. The brightness is around the same, if not worse. And the resistor is smoking. Why is it not brighter? See, the RMS or effective voltage for a full sine wave is its peak voltage divided by square root of 2. But we have an LED diode which LED only passes the positive cycle through, and the RMS or effective voltage for that is the peak voltage divided by 2. So if a 120 volt AC which has 170 volt peak is half rectified, the RMS for that is 85 volts. which means if we still want a continuous 20 milliamp RMS current through the LED, we would need a resistor around 4.25 kilo ohms. Well, all I have is a 3.9 kilo ohms, so a bit more current, and we plug in. There you go. Now we have a brighter LED. The resistor is smoking too much though. Oop. See, that's the issue with driving LEDs with resistors, especially at high voltage. While the LED itself was consuming around 60 milliwatts of power, the resistor was consuming 1.7 watts and burned. So especially at higher power application, having a series resistor to control the current just wastes a ton of power. Like for example, if you want to take down a terrorist that's living in a tent in the middle of a desert, you don't nuke the entire desert. You don't nuke the entire desert, no matter how fun it might be. But especially in low voltage, low milliwatt power applications, who cares about a bit of power waste? Go ahead, use resistors for those. Which reminds me, we can use a capacitor to limit the current through the LED. As we know, capacitors and inductors limit the current through them due to their impedances, and they don't consume real power, which means they don't get hot when they limit the unless of course the voltage exceeds their limit. Let me see if I have a capacitor that can handle 120 volts. Hey, I found a ceramic 1 microfarad 250 volt capacitor that should limit the current of the LED to around 32 milliamps, which is a bit over the... And the LED is already dead. Next LED. Here a new LED. Are they dying? Let me see if I can extract an LED string from one of these LED light bulbs. Don't break in my hand. Ha! No injury. And here's what's inside a cheap LED bulb. A string LED and a series resistor to control the current. Something I said we shouldn't do. And it's broken, I wonder why. And the string LED is basically a bunch of tiny LEDs in series, so it would require a higher forward voltage to turn on. Hopefully this string is not broken and my capacitor can limit the current through it. Here we are. Ha! It is working now. It burned? Yeah, it overheated. So I would need either a smaller capacitor for higher impedance and lower current, or a longer LED string so that there would be much larger voltage across the LEDs, so less current. But anyway, you get the point. This is actually one of the ways they drive LED strings in some of the light bulbs, and the good thing about capacitor is, again, it doesn't consume power. Now, what do we use to turn an LED on and off? A switch, of course. And what do we use for a switch? A transistor that can be a MOSFET or a BJT. We just send the on-off signal to the input of the transistor and the LED turns on and off. Here's my 5 volt supply and the circuit here. Don't mind the burned breadboard. I'm using a MOSFET, so if I hold the gate and touch the 5 volt, bing, the LED turns on, and touch the ground, it turns off. Bing, bong, bing, bong. Of course, we can use a microcontroller to drive the LED, but here I'm using a function generator. Now let's see what happens when I increase the frequency. Somewhere above 60 Hz, we stop seeing it flickering and it becomes continuous. But as you may have noticed, it's half bright now. This is because, same as when I was driving the LED with the AC line, although we don't see it, the LED is only on half the time, so the average brightness is dimmer. We can use this technique to adjust the brightness of the LED. See, if I decrease the duty cycle so it's off most of the time, it's dimmer, and if I increase the duty cycle, it's brighter. This is the simplest way to adjust the brightness, which almost everyone uses. Now you might ask, why don't we just tune the voltage across the LED to adjust the brightness? Didn't I already tell you? A little bit of voltage change across the LED results in huge current change and so brightness. So it's much harder to do. It's much easier actually to adjust the current through the LED, which translates in voltage across the LED, so some could say we are actually tuning the voltage across. Whatever! Here's a simple example of a current source circuit with a BJT NPN transistor. If we provide a fixed voltage to the base of the transistor minus the 0.6 volt drop on the base emitter, there will be a fixed voltage on the resistor at the emitter. So there is a fixed current running through it, which is almost equal to the collector current of the transistor. So almost no matter what load you place at the collector of the transistor, even if the supply voltage changes, the current through the load remains around the same. So we can place an LED as the load to make sure its brightness doesn't change with the change of the supply voltage. And we can tune its brightness by adjusting the base voltage. Here you go, I'm changing the base voltage of the transistor using a potentiometer, and the current, and so the brightness changes. All good and dandy for low power applications, but for high voltage, high power applications, we want something more efficient. So we rely on capacitors and inductors, or a switching power supply. Let me harvest another LED string first. These LED strings require tens of volts to turn on because there are so many LEDs in series in them. But let's see if we can turn it on using 5 volts. Here is a simple voltage boost circuit with a MOSFET transistor as the switch. The switch being fully on or off minimizes the power consumption over the driving circuits. When the switch turns on, the inductor falls between the power supply rails and the current through it rises, charging the inductor. When the switch turns off, the current through the charged inductor has momentum and wants to continue going. So the voltage across it shoots up so high, it turns on the LED string. It pushes its current through the LEDs, dissipating its energy quickly until the next cycle. So the LED pulses on fast, so fast we can't see it blinking. Here I threw the circuit together with whatever component I had. The LEDs are here, a 47 microhenry inductor, transistor, my 5 volt supply, and a 20 kilohertz PWM at low duty cycle. And if I turn on the supply, the LEDs don't turn on, but there is some noise. Looking at the output though, I see every time I turn the transistor off, I have spikes of 100 volts, which is apparently not enough to turn on the LED. But increasing the duty cycle and the on time, I should be able to increase this voltage. There you go. And my LED string is on. What is that, 250 volts? So I guess there might be spikes of high current through the LEDs, but at a very low pulse width. That's why it doesn't blow up. Remember, although you can send a certain amount of maximum current continuously through the LED, you can send maybe 10 times of that through the LED at short intervals. As long as the component doesn't heat up above its burning threshold, you can increase the current through it to much higher than the maximum continuous levels, say by pulsing the current. Of course, we can increase the PWM frequency so that the inductor current never drops to zero for a more continuous operation. For such switching circuits, we can control the output current by adjusting the PWM duty cycle. So we can place a fancy feedback and controller to accurately adjust the output. Good. But who cares about 5 volts? Let's see if I can run it from the 120 volt AC. For this circuit, first we rectify the 120 volt AC with a full bridge rectifier and a capacitor to get around 170 volt DC. When the switch is on, the current flows through the LEDs into the inductor, charging it. When the switch turns off, the inductor pushes its current through the freewheeling diode back into the LEDs. And again, we can adjust the current by changing the duty cycle. Here you go. Well, the components I'm using are much larger than they need to be, but that's all I have available. Every single time I forget that the ground of the scope is connected to earth, and I end up shorting it to the live. You know what? I'm going to connect the live and neutral of the scope only to the same power lines that are powering the circuit. No earth connected. Simple as that. It's not good to leave the transistor in an unknown state when you are powering up the circuit. See, if we leave the gate of a MOSFET floating, its voltage could accidentally be high, turning the transistor on, shorting stuff when we don't want to. So, in general, it's a good idea to have a large resistor between gate and source to make sure its voltage is zero when it's not controlled. Trying again. Please don't blow. We have what? 160 volt DC? 20K signal confirmed at very low on time. Connecting the signal. Very slowly increasing the duty cycle. Oh, I can see the LEDs blinking. I'm doing it! I'm doing it! God, I'm sweating like a pig here. It's getting brighter. Let me lower the frequency. It works. To turn it off now. We did it, guys. That was nerve-wracking. I was using a flash capacitor to clean up my rectified voltage. I guess it's a good idea to discharge it now. Oh, jeez. Well, all these circuits were just examples to give you ideas. There are a ton of different driving mechanisms out there you can search and find. And regarding the relationship between Event Horizon and LEDs, thanks to my sponsor Audible, you can start listening to exclusive Audible originals from top celebrities, experts, and exciting new voices, on top of an incredible selection of audiobook titles across any genre in existence. For example, as someone who likes to listen to stories when I'm droning through daily chores, I like to listen to the new audiobook I'm Glad My Mom Died by Janet McCurdy in her own voice. You know, just to make sure my daughter doesn't feel the same way about me after I die. And as a new member, you can get it for free, signing up from audible.com/electroboom, or in the US, text electroboom to 500 to sign up and try the first 30 days of Audible for free. And with your membership, you also get one free title every month, as well as access to the ever-growing list of titles and new favorites and formats, like the exclusive Words music series or podcasts. Just slap the Audible app on your phone and keep your brain busy with your favorite title anywhere you want at your own convenience, while your body is free on autopilot, droning through whatever. And thank you for watching.